Cool. We defined the principal log which wrote like this as follows. It's log to the base e, which just means the real log, the log on the real numbers of the absolute value, plus I, and then the principal argument of z, where the principal argument is inside this range minus pi to pi, right? And when we do this, then we have a perfectly good, well-defined function on the complex plane. Take away the negative real numbers. So defined and holomorphic on the complex numbers, take away this thing. So this means the negative real numbers, right? Because we have an issue when we go all the way around. So this is 0. So when we go all the way around, then we can't cross this because we have a discontinuity, because the principal argument goes from pi to minus pi here. So it's not holomorphic on the entire complex plane, but on this slit domain, it's holomorphic, right? So previously had to be somewhat careful when we did anything to do with log, that what log we were talking about firstly, and that we don't go over the place where there's some kind of discontinuity. But now we have the possibility to define a much more general log. So theorem, given any simply connected domain I'll put that over there. Omega, we can define, which has some properties, that contains one but does not contain 0, we can define complex log which is depending on this particular domain. So I'm going to write log of omega of z such that the following is true. So 1, this is a holomorphic function. On omega and d by dz of is 1 over z. Second property, e to the z, because it is indeed an inverse to the exponential function. And the third property, so this is how Stein words it, but later I'm going to ask you exactly what he means by this. So near, or for real numbers, so when it's a real number, then it is just equal to the natural log that we know from calculus. Okay? All right, proof. Let's put it here. Proof. All right, so what is the big deal about having a simply connected domain? It's that we can have any two paths with the same endpoints being homotopic and therefore have the same integral. Yeah. Since we are excluding 0, the function 1 over z is a nicely holomorphic function on our domain. Yeah. So let's define log of omega. Actually, I'm going to write f of z because it's just easier to write this. And later I'm going to say f of z is this log omega of z. So define this to be the integral of L of, where do we want to start? We want to start from 1. So L of z of 1 over z dz, where L of z is any path from 1 and ending in z. Yeah. So this is well defined. Yeah. And the first property, that d by dz of f of z is equal to 1 over z, is exactly the same argument we did before. It's exactly the same argument. Yeah? Because we just define up to z like this, and then we have this z plus h, right? So then f, maybe for consistency I should have written capital F. Let me write capital F, because that's what I used for the primitive before. Then capital F of z plus h minus capital F of z is just this integral over this little line segment of 1 over z. Oh, 1 over w, since we've picked z. Right? So exactly the same argument will give you this thing. Everybody happy with that? Yeah? Okay, good. So, this we believe, point 1 is not difficult. Yeah, point 1 is not difficult. Okay, point 2. Point 2, we want to show this. So, now, for I. So, it's equivalent to showing this. So, equivalent to showing that z to the minus 1 e to the, and we're calling it capital F, right? Capital F of z is equal to what? Right? If we can show that, then that's the same as this. Yeah? Right, so we're going to show that by differentiation. So, first thing we're going to do is show that when we differentiate this expression here, it's going to be a constant. So look at this. So we do this thing. Maybe I want to do it the other way around. I do want to do it. I'd rather differentiate e to the minus f. This thing is also the same as this thing, by the same reasons. Yeah? So let's make our differentiation life easier. If we differentiate this thing, what happens? Then by the product rule, we just have e to the minus f of z plus z e to the minus f of z, and then minus f prime of z. Right? And f prime of z we've seen is 1 over z, so then that thing just becomes e to the minus f of z minus e to the minus f of z, which is 0. Yeah? Cool. So the derivative of this thing is 0, right? And it's defined holomorphic on a simply connected set. Yeah? Therefore, the entire thing is constant. The entire thing is constant. And the only thing is to show that this thing is actually equal to 1. When we show it's equal to 1, then we're done. Yeah? But if we stick in the value z equals 1, so at z equals 1, what happens? We have 1 e to the minus f of 1. What is f of 1? What is f of 1? Someone who hasn't spoken yet. What is f of 1? Look at the definition. What is f of 1? It's 0. No? So then this is just 1 times e to the 0, which is 1. And therefore, that is what this constant is equal to. Right? So we've shown that this thing is a constant function, and that constant has to equal 1, just by sticking in z equals 1. Yeah? And therefore, this is shown, this is proved, which is proving this. Yeah? Cool. Everybody happy? All right, so we've proved 1, we've proved 2, now we're going to prove 3. I'm going to raise the board, think about how to prove 3, and I'm really interested to hear from someone who hasn't spoken yet. Okay, so point 3. The claim was that this complex log we've defined on the real line near 1 is actually equal to just the standard log that we know. Yeah? Okay, tell me why. And you have the right to take near to be as near as you want. So near can mean anything at this point, and then we'll think about what it actually means. So tell me why. I mean, how did we define our thing, right? How did we define it? We defined capital F of z to be the integral of L of z 1 over z dz. Yeah? So our path could well be just on the real line, right? So if this is 1 right here, yeah, then since it's an open set, there is some ball which is entirely contained inside omega, yeah? And then for any number on the real line inside this ball, we can indeed take our path to be just a straight line going towards it, right? Yeah? Okay, and then keep going. So what's the consequence of that? Yeah. F of z is exactly, this is exactly the definition of, let's write it like this, dx. Let's write it like this. This is exactly the definition of the natural log, right? This is how we define natural log, yeah? Which is the natural log. Okay. Cool. All right, so example. Let's put 0 here. Let's put 1 here. And then let's take this thing. And let's do this. Okay. So this is the real line. Yeah. And let's fill this out so that we see what we're talking about. So according to our theorem, this guy right here has a complex log, a well-defined holomorphic function, which is a complex log. So take omega as shown. It is simply connected. So we can define a complex log. All right. So what's going to happen to this guy? Well, if we just do this thing that we did before, when we just figure out what complex log has to be, so the most general form of complex log, so general form of log of z is log of z is equal to log to the base e mod this plus where arg is this multi-valued function, right? So, oops, there's an I here. Arg of z is equal to the principal argument plus 2 pi k for any k belonging to this thing, right? This is what we figured out when we discussed what complex log has to be, right? And the issue is we don't like it like this because this is not a single valued function, right? Yeah. But the claim is now we do have a single valued function, right? Yeah, on this thing. Yeah. Okay. All right. So around one itself is pretty clear, right? What about here? What will the value be around here? So there's no way for you to tell me, what the length this is. So tell me about the imaginary part of complex log, depending on this domain. What will the imaginary part be here? Just here. What will it be here? Given that on the real line, we have this just equal to the standard thing. So the complex part is 0 here on the real line. What will it be here? Come on, this can't be hard. No. What is the argument of a complex number around here? It's pi, because we're going anti-clockwise, yeah? Yeah? So it has to be equal to something very close to pi, right, as we approach this thing. And previously we had to be careful, because on this line we had a singularity, but now we don't. So actually when we're on the line, it is still perfectly fine. It's a holomorphic function, it's continuous, therefore it actually has to be equal to pi on the line, yeah? Okay, what about if we move a little bit down? What's it got to be? Well, it still has to satisfy this, right? It still has to satisfy this, because that's just what happens when we just differentiate stuff, right? So what does our complex log have to have for its imaginary part if we move down a little bit below this line? well, if it was negative pi, then there'd be an issue, right? What would the issue be? Can we just do this? Right. So it can't be negative pi. Yeah? So what else could it be? I mean, it has to be some value inside this set, right? Because that's what we know. So which one does it have to be? Louder? No? If we had 3 pi, what would we do? We'd go, this is pi. If we had another 2 pi, then we'd go all the way around again to the other side. Right? So we are just a little bit below the real numbers. Right? So if we had 3 pi, we'd actually just be on the real numbers itself. Yeah? Pi plus something. What something? You don't have to tell me exactly what the something is, just tell me about the something. Yeah, pi plus a little something, right? It has to be pi plus a little something. Because it's a holomorphic function, it's continuous, right? Yeah? So the argument, or the imaginary part of this thing always has to belong to this set, right? Always has to belong to this set. Yeah? Yeah. But the only way that's possible, and for it to remain continuous, is that as we move from here down a little bit, then we just increase the angle by a little bit. Yeah? Cool. All right. So that's what happens there. Yeah? And we're going round and round and round and round and round and round and round. What is going to be the imaginary part of our complex log right here? Two pi, right? Because this argument, this imaginary part is changing continuously, right? So we go from 0, pi, a bit beyond pi, yeah. And at every point, it is just the argument of the z. It is one of these values here, but it has to change continuously, yeah. It has to change continuously, and the only continuous choice of the argument of z as we move around like this is to go like this, and then out here at 2 pi. Yeah? Cool. All right, what do we have when we move a little bit up like this? What do we have now? Yeah, 2 pi plus a little something. Yeah? And as we move around like this, like this, like this, like this, like this, where are we here? What do we hear? What is the imaginary part of our complex log when we're here? Someone else. It's 3 pi, right? What about here? What about when we're here? What is it now? 4 pi. What about here? So I'm going to write some of this stuff down now. Let's go. It is indeed also 4 pi. Tell me why. Tell me why. Right. So the argument is continuously changing, right? Yeah. And has to go back to this thing, right? Has to go back to this thing. Yeah. There's no way it could do a whole 2 pi because we don't do 2 pi loop in the argument here. We're only going up a little bit and down, right? And then this thing again has to be 4 pi. Yeah. But even if we did go all the way up and down, it still would be okay because we reverse that. So if we had something like this, oh, damn it. This thing here would still have its imaginary part be 4 pi because we've gone all the way up here, right? And now we're going to have 5 pi, but then we're going back. We're going back, and now we're going back to 4 pi. Yeah? Cool. Yeah? So now we have, say it louder. Yeah. 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 Just think of this as for any z inside here, you have to continuously define this angle, okay? You have to continuously define this angle. But you have the right to take it over the entire real numbers, right? You're no longer restricted to minus pi to pi or anything. You can go anywhere you want. So indeed, as you go like this, then yes, you're gonna take another value of 2 pi every time you go counterclockwise, and then you unwrap it going clockwise like this. No? Cool. So we have much more freedom, much more power in our ability to define a complex log. Yeah? We can define complex logs now on any domain that excludes 0, which we want to exclude because then there's going to be a singularity there, so it won't be holomorphic. We want to include 1 just because it's convenient to include 1, so we can take that as a starting point and have something which is consistent with the ordinary log on real numbers. Yeah? Okay, now answer this question about what does Stein mean by numbers near 1, which we have that this is true. In what sense is this true for numbers near 1? Previously, we showed it was true if we have a small ball around here, right? Tell me precisely when is it true. I mean, think about the argument we did here. Think about this example. Okay, so you claim it's true here. Yeah? Does everybody agree? Yeah, and indeed it is true here because this argument works fine here, right? Yeah. If we just take the connected interval on the real numbers that contains 1, right? That is, let me say that more completely. If we intersect the real numbers with our set, we're just going to get an open set on the real line, yeah, which is made up of the union of intervals. We'll take the connected interval that contains 1, yeah, and then that thing we can do exactly this argument on, and then on this interval here we are fine. Okay, now the second part of the question, what about other parts where we wrap back, where we wrap back and then hit this thing here? What about this thing? Is it true here? Definitely not true. It's definitely not true. Yeah? What about this thing? Is it true here? Definitely not true. Now let's think about Laura's suggestion. What about if we have a little interval like this, and then we can do some funny stuff, whatever, but then we go around and we go back like this. So this is 1, 0 is out here. We know it's true here. Is it also true here? Yeah, it's also true here. It's also true here.